Hi everybody, my name's Chase. I've been part of the TWIML community, kind of in the background for a while, but there was an opportunity that came up a few weeks ago with people interested in doing a meetup for learning reinforcement learning. And myself, Carlos, and Harish kind of decided on the David Silver University College London course, I believe, on reinforcement learning that he presented a few years ago, I think 2014 or 2015, that we'll be using for videos. So this first meetup really just covers the first lecture, which is kind of a high-level introduction to reinforcement learning. My background, I'm a data scientist. I work mainly in like the last mile logistics space. Well, I think one of the interesting things about reinforcement learning is that it can be applied across a wide variety of problems, which is one of the reasons it interests me. Mute everybody there. So as we go through this, I think we'll see the large amount of problems that it can be applied to. Let's just go ahead and get started. I want to take a few minutes up top just to go over the kind of what the resources available in this meetup, its learning group, how we might desire to share resources amongst ourselves, ask questions, those types of things. Then most of this time will be spent going over the interview of lecture one, and then maybe a few minutes at the end just for people to hang out, ask questions, talk about their interests in RL or other things to get from the meetup. I think in general, we can be a bit flexible on how we exactly want to run this, but I think from my experience, at least, to get the most out of these types of things, it's helpful to at least have watched the video beforehand. And for the more technical videos and lectures that we'll be watching, kind of prepare any questions that you might have beforehand. There's a lot of brain firepower within this group, a lot of expertise and from a lot of different fields. So definitely the person that is leading the video lecture or leading the overview of the lecture, like I am today, will have like a good feeling of most of the things being covered, but that is, I mean, they're by no means expert in that. So kind of getting questions from the group is a good way to help everybody learn. For the schedule and resources, Sam was nice enough to help hook us up with this GitHub link, or this GitHub repo. This is just a screenshot. It has been updated, I think, since I took these screenshots. So there's links to resources in here. As I mentioned earlier, we're going over David Silver's course in RL. He's part of the DeepMind team out of Google. And so he taught this course at University College London, I think, before he went on, semi-permanent leave there. So that's going to be for the first part of the course. And the second part of the course, we're going to be going into OpenAI's spinning up RL, which is basically like a quick way to get started within deep reinforcement learning using some of their resources. The text we'll be using mainly as a reference is kind of the standard text across most of these courses, which is Sutton and Bartow's Introduction to Reinforcement Learning. The nice thing is there's a free PDF version of this available online, which is actually updated just this year. So it's a rather old textbook, I think originally from the 90s. I got a refresh in 2018, and there's a new printing out in 2020. Harish, Carlos, and I went back and forth over which course we wanted to use to kind of base this meetup off of. We ended up on this, David Silver's course, but there's a few more out there. I listed a couple down at the bottom here, which just Stanford's CS234, which is kind of another introduction to RL course that has lecture videos available. Then also Berkeley CS285, which is Intro to Deep RL. So those are available. And then this will keep being updated as we go along. So each week we'll have the link to the video and the slides. These slides listed here are David Silver's slides. I updated with the slides that you're looking at here. I guess as a note, it's probably not important for the presenter to create their own slides. We can obviously just go through the slides that are posted. It's just I did a little bit of little memorization, because I think his lectures are usually like an hour 15, an hour 20 minutes, and so we're a little time constrained, so there's a lot to cover. So but yeah, so all the schedule keeping updated, and as people are posting links in the meetup, or in the what is it, the RL meetup Slack channel, I'm trying to drop them in here. I think we can spend some time at the end talking about this Calvo competition, other things that we might want to do to you know, get more hands-on learning to RL. All right, so does anybody have any questions on any of that before I go ahead and jump into the lecture one material?
I have a question.
Yep.
Could you say anything about how you determined not to use the Berkeley or Stanford course, how they're different?
So we did have a back and forth. So Stanford's course is focused a little bit more on the control side of things, and Berkeley's course is an intro, like it's a very quick dive into deep RL, whereas this you know, this course that we're focusing on, I would say it's a bit of a gentler introduction to the topic. So that's one of the reasons we decided upon it. It's also a slightly shorter, so we can maybe speed up the process, or speed up the process as far as like the number of meetings we have to have before, you know, covering the base material before jumping into the coding part. Yeah. Any other questions?
I have a question just in relation to the RL book. There are I think at the end of each chapter there are questions posed. Will we be covering them?
I think we can. Yeah, I think that's actually that's a pretty good idea. Like things to kind of like, you know, challenge your comprehension that we should probably be covering as we go along. I think I didn't prepare anything today. We can definitely look at them at the end of today's lecture. But yeah, I think that's a good idea. Maybe that's something we figure out how to do. Like post one or two questions in the Slack chat or something, just to have people like know that we're going to be focusing on these one or two questions, and then we can talk about it. Does that sound good? Or any other ideas? All right. Yeah, if there's no other questions, we'll just dive into the overview of lecture one in his course, which is just broad level overview of reinforcement learning, which mainly has 3 points, which is basically introducing the reinforcement learning problem as like a suite of problems, then going over agents, and then focusing on like the different flavors of problems, you could say, in reinforcement learning. So this slide was showed by Silver, mainly just to emphasize like the broad class of problems that reinforcement learning can be applied towards. Really borrows from a lot of different you know, research fields in academia, from computer science, psychology, and, you know, mathematics. It's one of the reasons why I was drawn to it. So I sit kind of more in the operations research space, though that's not my technical training, but that's kind of more of what I do now. And so it's nice to have access to a, you know, suite of algorithms, a suite of approaches that can kind of borrows ideas from all these areas of research and allows you to apply them to a wide array of research. So the most popular one that people have probably heard about is just the application to reinforcement learning to playing games through either like AlphaGo or chess. Alpha StarCraft is something I'll like briefly touch on in a minute. But so any sequential decision making problem is something where it does quite well. And he goes on to talk about how reinforcement learning as a problem is kind of it interlinked with many other problems in machine learning. This is actually kind of a mislabeled figure. Machine learning is really this outer circle that is encompassing supervised, unsupervised, and reinforcement learning. But it's definitely like almost another branch of machine learning. If you think about you know, supervised learning with trained and labeled data, and unsupervised learning trying to categorize or you know, group certain things through automated means. But then reinforcement learning is kind of another problem where you're dealing with like sequential decision making. But as far as characteristics of the reinforcement learning problem, it's kind of the viewpoint that we're taking is we're always thinking about acting as an agent, where agent-based modeling is something that's pretty old, but maybe not so old in the machine learning space, where you're acting as an agent, as a person, as a machine, or something in the world that is trying to make decisions its own. So you don't have any supervisor telling you what to do. In reinforcement learning, you're only seeing the rewards of your actions, and you're trying to maximize your rewards in some way. Some interesting things about the problem is that you can have delayed feedback. So the rewards that you're interested in, you may have to delay your gratification in the short term in order to have a long-term, much larger reward through delayed feedback, and because of that, order and time matters. So in reinforcement learning, basically the steps you take, each step is and we'll get into independence and things later, but each step has an impact on the future rewards you might see, and so that we'll get into exploration, exploitation, and how we traverse down familiar paths versus explore the unknown, and how that can impact our reward for futures. And I guess the last important thing is that the agent interacts with the environment, which is super important. So I think this is probably most obvious, like the robotics realm. You can act as an agent where the agent is a robot. So you're seeing the world in some way that the robot does, and you have to interact with that environment either by going forward, backward, turning, rotating, all those types of things. So how you interact with the environment is going to impact your the rewards that you see, and also impact the next data that you end up seeing. Yeah, go ahead.
Yeah, is it David Silver? Is that his name?
Yes.
He did make a point of the delayed feedback. And I was wondering, how that naively it seems that conflicts with Barton and Bartow and Sutton's quote: on each time step, the environment sends to the RL agent a single number called the reward. But there is delayed feedback. But you always do get a reward, right, for every time step. So I guess it seems like those might be in conflict because feedback is delayed. But I guess maybe the answer to that potential conflict is that the reward you get might not actually incorporate immediately the consequences sort of your action, I suppose, right?
Yeah, correct. I think that's a really important distinction. If somebody else wants to jump in, I can. They're
yeah,
free to do so.
What I got from that is essentially kind of what you summarized, Tony, is basically at one step, we might have like a huge reward based on the environment at that time, but after a certain number of steps, it might actually have been taking the wrong direction. So the overall cumulative reward would then actually be negative. So it depends on the goal, I suppose.
Also,
so that's what he means by the delayed feedback.
And couldn't you can still get your reward, but it could be zero. I mean, I think in a lot of cases, right, depending on how you set up a certain problem, you can get, like if you're playing some card game, for example, or chess, and you only get a reward if you win the game, then you're going to take a lot of rewards or a lot of actions where you get zero rewards. But I think we're ultimately trying to maximize the sum over all these rewards, these delayed rewards in a lot of cases. So I think, at least in my mind, that's how I'm making the two work together. There's just zero rewards basically in certain situations.
Yeah. Also, there was this cool example question asked about what if we're trying to optimize for how to do something very fast in terms of time. So the reward at each step is -1, but you don't really have a feedback on how fast you are until you come to the end.
Right. Yeah.
Yeah, and we'll see later, a little bit later in this, and just this overview of how you like kind of weight rewards. There is some trade-offs between how you value a reward right now versus one in the future, which we'll briefly touch on today, but I think we'll go into a lot more detail in one of the following lectures. And so I'm just going to give a couple examples of reinforcement learning. Probably not spend too much time on this since I think most people have probably seen them. I chose some different ones than what are in the lecture, just based on what I thought were interesting at the time. So I don't know if any, well, and we'll see how how video plays over Zoom, but not share my audio there. But so I think most people are familiar with AlphaGo, where the DeepMind team at Google basically taught a reinforcement learning agent to play Go and beat the world's best masters. And they also did the same thing for StarCraft, where this is a game I probably played a lot about 8 or 9 years ago. But it's basically it's a different form of game where it's a real-time strategy game, so you can see things are moving in real time. And here, this blue player is actually Google, or the DeepMind player star, and the spread player is original that it's playing against. And it's a much more complicated game than, in part because it's done in real time. There's a lot of different variables you have to control for, and I just wanted to show as like an example of somewhere where we can use reinforcement learning to train very complicated algorithms that can play things like even StarCraft, and obviously we're interested in using reinforcement learning for robotics and other things. But in here you've got like this blue player, which is a computer, going in and playing very lifelike or like human-like actions based on its its training runs that it's done in order to basically train this agent in order to play this game. And there's commentators for these esports games, and he's going on and talking about like how complicated this AlphaStar, this computer player, is at managing the resources at a time, doing all these like very fine micro movements that a human, like the top level human, like the person he's playing against, could do, but it's very hard to sustain over time. And in the end, like this, spoiler alert, the computer AlphaStar goes on to win this particular game, and actually went on to defeat like some of the world's best players in this game over like a 5-game series. And obviously this is a huge effort that wasn't just reinforcement learning, but reinforcement learning was like one of the foundational aspects which this agent was built upon. So I think that's one interesting game that can be applied to. And I think we hear a lot about reinforcement learning being applied to games. Something else that it's often applied to is robotics. And so this is just an example. This is actually somewhat old in the realm of machine learning, actually, but from all the way back in 2017, where we have this is a drone. Let's see if I can find a better spot to start. This is a drone, basically, that I think they call it like trail drone or something. They basically train this drone to fly along like any trail that has like similar features, right? So you have like a path in the middle, you have some obstructions on the sides and above it. And so this is a drone that has movement in 3 dimensions, so it can go back, forth, side to side, and up and down. So it's a little complicated, but basically training this drone in order to see obstacles along the path, and also most importantly see the path through reinforcement learning training. And it's not, you can obviously, this is moving in real time, it's not moving very fast, and so obviously one of the trade-off things that you have to do, especially with older NVIDIA GPUs that are used, like onboard processing units that are using these drones, but it's like it's a drone that hasn't seen this trail before, and it's able to fly pretty well based on its training. I think there is one example. You can, so SLAM, simultaneous location, and somebody from Robotics can remind me what SLAM stands for, but basically being able to see obstacles along the drone path, and you'll see here it's coming up and sees an obstacle, an obstruction in the path, and then stops. And just one example of reinforcement learning being applied to fairly complicated real world problem. Oh, thank you. Yes. Simultaneous localization, and mapping. Thank you, Harish. Yes, I knew what it stood for once, and then obviously forgot on the spot. All right, so we'll move into. I guess maybe just take a second and let anybody share like any examples of reinforcement learning that maybe perhaps they're working on, they're interested on, that maybe aren't obvious or I didn't cover. If not, Yeah, go ahead.
Okay, so yeah, so I'm like completely brand new to RL. I mean, I just started learning about deep learning essentially just maybe a year ago, and mainly got into it through Fast AI. My interest into RL was mainly triggered by what happened, I think in April, when Google developed a reinforcement learning algorithm for chip design, essentially AI, building AI for itself. That was very cool. That's a problem that's I've been interested in, like, how does that happen? And until then, actually, I hadn't had like a concrete example of a real world application for reinforcement learning. I mean, my idea of it, of course, it is like not very informed, was that it was, yeah, mainly the AlphaGo kind of stuff, games and things, but that made it very concrete. And so that really spiked my interest.
Adrian, did you want to say something?
Oh, yeah, thanks. So I'm completing a master's in data science, and for my thesis project, I'm exploring reinforcement learning applied to cryptocurrency trading. And one of the issues that I'm grappling with is with your earlier slide, where for a reinforcement learning agent to observe a new state, that I think it was even earlier. But when a reinforcement learning agent makes an action, it should observe a new state. And I think for the algorithm to work, there's an assumption, not an assumption, but it's required that as a result of the agent being in a new state, it has made some impact on the environment to be in that state. So, for example, in a tic-tac-toe example where a reinforcement learning agent places an X, it's quite clear that it's changed the environment and it's in a new state. But if you think of a trading example where you may place a trade, it's not clear if that trade that you've placed has impacted the environment in any way. It may or it may not, and it's not clear what that measure might be. You'll observe a reward, of course, but it's just it's difficult to I guess to discern if the agent will learn or not, because it's not clear if, as a result of its actions, if it's changing the environment or not. Like you could say that, yeah, if it makes a trade large enough, if it's buying 1 million shares or something like that, then yeah, it is going to impact the price. But for smaller trades, will it or not? So there's just some questions around that that I'm just working through.
Yeah, and I think it's interesting, like especially taking reinforcement learning past, the simple games like your tic-tac-toe or chess is, it's complex, but it's actually, simple for a computer to learn, and into real world examples. So I can, I guess from my experience, well, not my experience, but within my company, we have some people looking at using reinforcement learning to basically act as you think of it as a recommender algorithm for customers as they're shopping through an application, using that close to real time sequential data in order to make suggestions about what they might like to see next. That's one example, and then from my own personal experience, I'm interested in applying this to like a routing problem, or maybe it's like a dispatching problem. So if you're a taxi dispatcher, I don't work for Uber, but I'll use this as an example. If you're a taxi dispatcher, how do you decide where to place your drivers, your cars, within the environment, within the city that you're operating within, in order to most effectively serve your customers. And so if you have a long string of data that you can use to kind of build a training data set for that, and then also obviously observe it in the future. That's one thing that I'm interested in using it for. Not quite sure how I do that yet, but that's why I'm here. If I knew how to do it, I wouldn't need to be in this course. So, all right. So I think if anybody else has something to say, please go ahead.
I have a quick question. Hi everyone, my name is Mason. For the trail drone, so this is an RL course, right? So I guess in my mind, the drone would have had to try to fly this trail like a bunch of times and then eventually learned how. Is that how they, or I guess, do you know how they did it? Is that how they did it?
I don't know exactly how this team did this, but I know I have a passing familiarity with autonomous robots, which somebody on this call probably has much more than me, so I'll say it briefly and let somebody else say it. But you can with this like SLAM, the simultaneous localization and mapping, like you can learn your environment, like a new environment, without having to actually train on this specific trail. So it can learn from similar environments and apply that to a new environment.
Sure. Okay, cool. Very interesting. Thank you.
Chase?
Yep.
For that logistics domain you talked about, it might be simpler, though less compute efficient, to use evolutionary algorithms for that. Have you considered that?
Yeah, we're actually looking at a suite of approaches to do this problem. So RL is just one. We are also looking at evolutionary, and then also probably some much more classical optimization or operations research problems.
Hi,
okay.
I'm Vishnu. I work at Credit Karma. I work on recommender systems at Credit Karma, and the way our business model works is we recommend financial products to our users. And over the years, we have added different types of financial products when it comes to, we've done a great job with credit cards and personal loans, but when it comes to some of the other more complex financial products like mortgages, we feel that we want to be with the members, and there's just like the way we think about rewards is very, very different. With respect to credit cards and personal loans, it ends up being more of a somewhat of an impulse purchase. But once you start looking at mortgage, you need to kind of go through the process of hand-holding our user through a long, unwieldy process. So we've been starting to think about like how maybe we can bring in reinforcement learning, because you get into the domain of some kind of sequential decision making. So we're trying to figure out if some RL stuff can help us out.
Great, thanks. Yeah, for the rest of the kind of overview of lecture one. So lecture one is pretty kind of definitional. So we're basically going over the major components of a RL system. So there's nothing too deep here as far as mathematical understanding, which is nice. So we can hopefully move through this a little quickly. But just to start off with, we'll talk about rewards. And I put up here the art of reinforcement learning. I think defining the right reward, or figuring out what the right reward is probably. I mean, I don't know from experience, but I'm guessing it's probably going to be one of the hardest parts of the whole process, because this agent is trying to maximize its total reward. So if you're trying to, you define your reward incorrectly, then you're going to be maximizing towards the wrong thing, and that can have real impact, especially if you're in a business setting trying to make business logic decisions with your RL agent. But as I think maybe it was Tony asked before, so. Reward as defined in Sutton and Bartow in most of these courses is going to be a scalar feedback signal that you get at a single step in your kind of sequential process. So R underscore T here. And so the kind of the aggregation, the summation of these rewards are the thing that you're going to be trying to maximize over time. Just some examples. So in kind of your classic game space, so AlphaGo, Go, chess, tic-tac-toe, checkers, or AlphaStar. So the goal is to win the reward, or sorry, win the game. So when you win the game, you get a large positive reward. If you lose it, you get no reward or a negative reward. So that's kind of easy to set up. But if you think of a complex game like Go or AlphaStar, do you get a negative reward when you lose a unit or lose a piece or lose one part of the move, or are you trying to optimize towards when your main goal is to optimize towards the end large reward of winning the game? As far as a trail drone goes, you have negative rewards here, probably don't run into anything or crash. you could have some positive rewards, like maybe you're trying to, you know, finish the course in the least amount of time, but then you kind of have to offset that with, you know, the potential catastrophe of running into something and then crashing and losing any possibility of getting that positive reward. Another example is just giving driving directions. So maybe your reward here is reducing your time to arrival. So positive reward, and then maybe that's measured in like legs of the trip. So the less time you have in each leg of the trip, the higher your reward is. And as I've mentioned a couple of times, other people alluded to, so reinforcement learning is really powerful and used in kind of in sequential decision making. So we're trying to choose actions that maximize our total future reward. So we're interested in steps, and these steps can be game steps, like, you know, each turn in a game of chess, or it can be time steps. You know, trying to minimize the time to get somewhere. You could also measure this in other ways as long as it's sequential. Important to note that these actions can have long-term consequences. So if you make, say you're driving and you make a wrong turn and you end up driving off a cliff, obviously that'd be bad, right? So we have to think of not just the next step that we're going to take, but also like the possible future steps that we could end up in from taking that next step. Because of this, rewards can be delayed, which we talked about a little bit already. And so it can obviously be beneficial to trade off short-term for longer-term rewards. So if my reward was to, you know, be more healthy, I might get more satisfaction in the short term from eating like the box of Oreos, but long term, that's probably not going to help me reach that reward or that goal of being overall healthy. Have some examples down here. So in the game space, so maybe you need to sacrifice some units to buy time or change an opponent's position. In the Alpha StarCraft example, in the trail drone, maybe you need to slow down to not run into things or potentially collide with something else. Personal health, which I mentioned, don't eat the cookies to feel better, so you can feel better later. And kind of starting now, I'll be copying a lot of images from Silver's talk. So he kind of paints this system of the agent and its environment that it's interacting with. And I think we've also touched on this already a little bit. So an action or an agent is taking actions at each step T. So this could be time or like a, you know, sequential step in a game. So what the agent does is it executes its action, it receives its observation from the environment, and then it gets its reward from the environment. And that all happens at step T. And there's an important distinction between T and T+1 here, especially when it comes to like the agent and its environment. So the agent does everything in its step T, and the environment receives that action at step T and then provides its observation and the reward at the next time step. And this is definitional. And so throughout this course, I think this is true. I know this is true in this course and also the Stanford CS234 course, but this reward that you get, and this observation happens at the next step. So when you take when you take an action at step T, you get the reward for the next state that you're going to be in. And yeah, so this increments at every environmental step. So you are, so you're basically, you're the brain in this case, or your computer, your robot, whatever is the brain. And so it's taking the actions, receiving the observation rewards from the environment.
Okay.
Yep.
Yeah, it was a little confusing to me. So I think the order is that it's opposite of what it is in the slide, right? Well, you talked about something being definitional, but the agent receives the observation and a reward from the environment. And those are the first things that happen, like when you turn the robot on, for example. And then it uses that and executes an action, right? It's kind of the opposite order of those agents' bullet points.
Yeah. So the way this slide is written, or the image is written on the slide, is it's kind of a reference point of how you want to think about it. So like this feedback happens instantaneously, but the way we account for it in if you want to think of it as an accounting system or in our vectors or whatever in our computer, in our programs, it's going to be like for the next, it's going to be the next index that we're going to be thinking about. But it does it basically happens instantaneously in like real time if you think about it that way.
But when you're programming, you have a loop. I guess you have an iteration, I suppose.
Yeah, so like at the end of your, so if you think of like, if you think of this as like a for loop, at the beginning of the for loop, you're telling your agent to take some action, and then that's going to put you in a different state, and that next state has a reward, reward and observation. The observation is of the state, and that reward is going to be of that next state, which is going to be the next state you're in. So then it's indexed to that t+1 instead of t.
Mm-hmm. Okay.
Yeah, which this is relevant. So history and states. This is a brief overview. State is just a function of the history that you've seen or that the agent has seen in the past. And states can be relative to what you are in the problem. So there's environmental states and agent states. I think mostly in this course, we're almost going to be solely talking about agent states. Though I think it's important to keep this distinction, this agent versus environment state, just in your head in case it does come up. But I believe for most of this course, we're going to be thinking about things in the agent state. And then there's also, Vishen, you want to say something?
Yeah, so I think once we start looking at like models, maybe the environment state also might start making sense, I guess.
Yeah, I guess we'll see based on the math that comes up in the later part of this lecture. But I think environment state obviously does matter. I think just if at least this is how I think of it. I think of like myself as being the agent when I try to think of these things. So I generally think of things as the agent state, but it can obviously maybe be beneficial for other people to think about it differently. But that's just how I kind of reconcile it in my head. But yeah, so the other thing to think about, so as the information state or the markup state, which is kind of the underpinning of probably the next couple of lectures, basically we make the Markov assumption when we're thinking about states. It basically means that the current state that we are in contains all the useful information from the history of the previous states. So in math form just means the probability of our next state given our current is the same as the probability of the next state given all the previous states that we have seen in the history of the problem.
I had one other question, comment. David talked about the environment emitting an observation on the previous slide, like it's the environment that emits an observation that the agent sees as input. But I mean, I guess I would think of it more as like a robot would be making an observation on its environment, and the content of that observation would depend on, what sensors the robot has, for example. Given the same environment, two different robots could make a different observation. It's not, you know what I mean? I wonder if that's the right way to think about it.
Yeah, I mean, that is a good way to think about it. I think it gets to the point of agent states. So the agent doesn't necessarily see the entire environment. And so this gets into the point of, I think maybe it was Adrian was, or somebody was pointing out before that the agent's action can change the environment. So under the assumption that the environment does not change, the environment is always emitting like the same observation. It's kind of how the agent sees it, which kind of makes the distinction between the agent state and the environment state. So if you're a robot with some sensors on it, you may only be able to see to the front and sides of you and not behind you, so you're not seeing the entire environment.
Harish here. So touching on the same thing, but Anthony, wouldn't that be just applicable for a robot, right? So say take a game for an example. The perception is the same thing, right? Like if you make a move, whatever the state that the current board, if you take a chess for an example, if you make a move, the state is going to be fixed. It's going to be the same thing. You have to get only one state, but when you have a system that's perceiving that environment, then yes, depends upon how you're perceiving, then that particular observation might be different.
Yeah, for something like chess, I think that would be different than.
Yes, exactly.
But I think probably a lot of practical applications would be more
Yep.
like a robot or game, I think.
Yeah.
Guitar game.
Yeah, I think there's definitely like a lot of ways you can cut this and think about it. It is a little confusing because you're trying to like keep, states, observations, and of two different things at the same time, and trying to think about how to like account for them in your both mental model and obviously in your algorithm model as well. So I think we'll get a little bit of clarity later on about which states we're dealing with for specific types of problems. I think for this introduction, it's not as important to distinguish to it, but I think just to follow up on what I was mentioning before about Markov states, I think the important thing to note here is that we'll make the assumption for I believe this entire course that both the environment and history states are Markov, so that they're the current state contains all the useful information about the past states in the history. Tony, did you have something else you wanted to ask?
Yeah, I think I'll be updating my mental model as we go along,
Yeah, it's complicated, I think, from like reading ahead one chapter, But to move along, so I think the next, well, probably spend the most of the rest of the time talking about the components of an RL agent. So this is mainly broken down into three core components: your policy, your value function, and then your model. Definitions are given here, but so we'll just step into these. So the policy is basically the thing that defines your agent behavior, tells it how it's going to act. And it's a map from the state that your agent is in to the action that it's going to perform. So you can have deterministic mapping. So given your action is going to be just a deterministic function of your state S, so it's not going to change. Or you can have a stochastic mapping. So your policy function is going to be conditioned on the current state you're in. So if you think of like what's like a classic game where you can move, north, south, east, west. If there is a, put it very simply, if you're on the south wall, you can only move north, east, or west, and maybe you do so with some probability for each one of those actions. That'd be like the simplest example of the stochastic approach. For the value function, just briefly, so the value function is basically used to predict the future reward that your agent is going to see. So once you're in a certain state, you want to evaluate the future reward from being in that state. And it's basically used to select actions. So you look at what the most beneficial actions to take given these different value functions. And we talked earlier about this, whether I can't remember exactly how we were framing it, but delaying gratification or delayed rewards, and that's what this gamma parameter is. It's a discount factor to basically give a weighting to future rewards. So obviously, the higher this gamma value is, the more important future rewards are to you, and this is going to be between 0 and 1 inclusive. Yep. Vishnu?
It would be interesting to think about the whole cookie example that you gave and what the discount factor should be for that.
Sorry, which oh, his like you mean the mice and the cookie example that he gave?
No, it's more like don't eat a cookie now for longer
Oh,
term health.
okay, yeah. So in that case, like the discount factor, if I'm eating like a whole entire package of Oreos because it makes me feel good, my discount factor is essentially well, I guess it depends on how we build our rewards here, but it's going to be pretty much 0. I only care about this immediate gratification of eating the cookies at RT plus 1, and don't care about how I'm going to feel at RT plus 2, T plus 3, etc.
It says like discount factor is it between 0 and 1 or?
Yeah, it is bounded between 0 and 1 here. And I think I haven't gotten into this because I haven't gotten into like the proofs around this, but there's some we choose it this way, and we choose this kind of geometric pattern for this because I've heard, I don't know this yet, but there are some nice properties that fall out of this that we'll explore later.
You want that to be a geometric series, so infinite sum of geometric series would still be a finite number. So that's the reason why and that geometric series holds only if gamma is between 0 and 1.
Yeah, that makes sense.
That's why it's finite.
Okay, so the model is an important thing here. It basically is a way that you can predict the next state that you're going to be in, and then the agent is going to be in. I kind of use you and agent interchangeably, which I apologize for. But predicts the next state the agent is going to be in and the board that the agent is going to receive its environment. So notationally, we use these calligraphic, or David Silver uses these calligraphic letters, so I try to follow that through. But so the, let's see, what is this? So this is basically predicting the next state you're going to be in. It's a probability that that state st plus 1 is s prime is conditional on the current state you're in and the action that you're taking. So the probability that you're going to go from s to s prime given the action A. For the next reward, the model is, let's decompose this. So the expected value of your reward that you're going to receive from taking action A from state S. So all pretty simple. So he laid out this maze example in his course. I just copied his slides verbatim right here. So basically, you have this maze where you have the start and a starting point and a goal, and your reward is -1 per time step. So you want to complete this as fast as possible in the fewest number of steps, and you can only move in those 4 directions. And your state is going to be that the agent is in one of these boxes. So pretty simple setup. And for this, so the optimal policy would be, or the policy here, which got something in the way here, sorry. So it's deterministic. So for each, when you're in one of these states, you're going to take the action here. So there's no stochastic policy here. So if you're in this square, you're going to move left. If you're in that square, you're going to move right. So given that you're actually starting here, you're never going to actually see these squares down here, given this is a deterministic policy. And so the value for each of these is, so this is the value model, so it's the value of all the future rewards. So when you're given a certain state, so this is simply like the number of steps you are away from the goal. So at both the start and this point, you're 16 steps away from the goal, and obviously just increments by -1 as you go along the path. And so for the actual model, so this is an interesting thing. So there are Model 3 approaches that we'll get into, but and if we're not in that type of environment, the agent may have an internal model of how the environment works, and know then how the actions change the states that you're going to be in, and then how much reward is going to be received from each state. So in this case, in this kind of maze example, you know what the entire environment looks like, so the agent knows pretty much everything. And so this grid layout then represents the transition model from one state to the next state, given some actions, and then basically the numbers here represent the reward, the R of t from each, or the R of t that you would receive being in each state. So it's the same. So you can imagine if this were set up slightly differently and you had a different reward structure, maybe when you're in, for whatever reason, when you're in this box, you get a positive reward. So even though you don't reach the end goal as fast, you want to visit this box in order to pick up whatever reward that may be. And so then you're the optimal approach would be different than the one that just simply get it done as soon as possible. Yeah, does anybody have any questions on that example? I went through it pretty quickly since it's also in the lecture as well. No? I just wanted to show this slide just to overview that there are like a lot of different types of agents that we can use when we're trying to do this reinforcement learning approach, which I think we'll talk about most of these in this course. The model-free approaches are, a very large chunk of research that I think we hit towards the end of the course. But depending on which one of those components that they have, either policy, value function, or a model of the environment, will basically kind of flow you into the tree of which approaches you're going to be taking, and therefore which algorithms you can apply to the solution of those approaches. I guess next we'll just talk super briefly about exploration and exploitation, which I think actually has already come up once. Is basically like how do we given an agent, how do we control it in such a way that it doesn't try to do the same thing over and over again and say get stuck in like a local maximum for reward, and actually explore its environment in order to get the best possible reward from the environment. And that's basically what the exploitation framework is used for. So the agent's actually, from a very naive perspective, actually discovering a good policy from its experiences with the environment, but at the same time, it doesn't want to lose too much reward in this process. So if you're thinking of, like, say the trail drone example, somebody asked earlier, like, does the drone have to fly through that same trail in order to build its model? The answer is no, but you can also imagine, like, when it's in a new environment, it might be more conservative its approach, say like how fast it goes in that environment, because it is trying to learn from the environment while exploring like a new trail or a cave or something like that.
Just curious, I'm just curious about the exploitation comes into picture when you're training, right? So when you kind of release the model in the drone example, would exploration and exploitation come into picture there too?
I guess at SLAM, yes, because but if you have, because like in a SLAM case, you're still unsure, you're continuously exploring the, you continuously update your system.
So you're actively learning there?
Yeah.
Oh, okay.
But in case where like, say for a game like chess or something where like the environment, like, you know that if you make this action, the reward in the other stage is going to be like this. So in that case, you just basically like you train it and then you just exploit or use the same, let the model do what it is.
The thing I would add is that if you have dynamic rewards, you continually have to do that, have to use exploitation.
Good point. Okay, thanks.
Thank you. And then, so when you're also thinking about the agent, okay, sorry, just looking at unmutes. You also have to decide like what type of problem you are looking at. So you can break that up into like the two simplest form, which is prediction or control. So if your agent is given a policy, then you are then able to evaluate the future reward from that policy. But then in the control example, which I think is more realistic to most use cases that we'll be talking about, what you're actually trying to do is find the best policy in order to optimize that future reward and potentially unknown environments, or just releasing it into the known environment with a lot of uncertainty. And that's, control is the thing I'm more interested in for my work, but there's probably plenty of use cases from the prediction side as well. So I'm just not as familiar with them.
One more question there, sorry.
Yep. No problem.
How does those words prediction and control kind of connect to those definitions? I kind of missed that link. Is there something?
So if you think, well, somebody else can hop in if they feel like it, but from my perspective, like, from the prediction standpoint, it's a more simple problem, because you have the policy at hand and you can set the agent in the environment at some state, and from there you're going to be able to much more easily predict what the future reward is, given that you start some state or in some state. That's where prediction comes in for me from control. It's basically it's release giving more agency. Well, that's a better word to use. More agency to the agent. Giving more. I'm trying not to say control. It's giving more resources or decision making over to the agent in order to explore and learn its environment in order to find the policy to meet its goals.
Okay.
Chase, can I go? I mean,
Yeah,
like,
yeah, great.
so like an easy example would be like in any control like setting, right? So you basically give some target or a set point that you want to like reach. And then basically you evaluate your set of actions so that you ultimately reach that point, or you minimize the error between like my current reward and my expected reward or something like that. So in your control, you basically find the best policy to reach that target reward that you want. But in prediction, you basically say, okay, I'm giving this decision. What would be the reward if I do this decision?
Right. Okay.
Yeah, I think it's a helpful distinction. Thank you. And that's I think I just looked ahead in my slides and we're basically at time anyway. But that's all I had on the silver lecture material that Silver covered in the first course, or in the first lecture, which is the introduction. So if people are able to stay on for a few more minutes, I think it'd be helpful to just have a discussion over like the resources that we'd like to have, kind of the approach that we'd want to take for this meetup. So I know several of you have already signed up to present one of these lectures, which is great. If you want, like, the best way to learn something is to teach it. So if you have something that you're particularly interested in and it's still available to sign up for, please sign up for it. They're the most current up-to-date reflection of that is in the Google Sheet, but I'll update that on the GitHub repo as well. But also just, yeah, go ahead.
Sorry, Chase. It would be helpful, I guess, like if you also update the link of the Google Sheet in the GitHub repo, like where they can sign up.
Oh, yes, good. Yeah, I'll do that. Yeah, and also, yeah, you're also always free to make a pull request if you really want to on that Git repo.
Okay.
But yeah, I will add the Google Sheet the sign up to the top of the schedule header.
And Chase, can you define a little bit more what is expected of the person who hosts? Like, I think you mentioned these slides were ready for you.
Yeah.
Yeah. So I mean, all the slides from David Silver's course are, I mean, they're free. So I made my own just because I don't know. So I do that, but but there's no reason you'd have to do that. So we could, I mean, the person would not need to make their own slides, but basically would have to, from my perspective, obviously understand the material to like the best degree they're possible before the meetup, and then just kind of present an overview of the lecture. And basically, it's an avenue to allow people to ask questions about what's covered. And as I kind of mentioned, it's kind of expected that everybody's going to watch the lecture videos before coming here. And I mean, there's some very smart people on the call that have understanding from a wide variety of areas. So kind of put together, we'll be able to figure out most questions people have during the course of the review. But yeah, so just basically watch the video or the slides and be prepared to like present an overview of what was covered in that lecture to the group is what all I think is required.
Cool, thank you.
I had a question. I don't know, do people know, I have little or hardly any experience with RL so far. Do people generally use libraries, existing code, implementations that already exist, and apply them to their problem, to their domain, the thing they're interested in? Or do a lot of people actually write their own RL code, implementing the algorithms themselves?
I think the key thing is to have a simulation environment. that is the key point I think a lot of people miss when they get into this space. And that's why OpenAI is so useful, because it gives you a bunch of simulation environments. The biggest problem you have is, how do you create your own simulation environment so that you can codify the observations or the states that you're going to get? That would be my suggestion.
Yeah, and I think that's a really good point. I think so some of us, like myself, my work actually has its own simulation environment, so like I could, or for problem I'm interested in, so that makes things easier. But I think then in general, like there are plenty of open source libraries for RL. It's not something that I think you'd have to build from the ground up.
And I guess like the DeepMind Acme package is an attempt to do that, as in like have like a library of all the RL algorithms in one place so that you can use if you have an environment for you to implement it on. But I guess like it needs like I need to explore them further, like if it's whether like if it's like implementable across all environments, or does it need the observations in certain formats so that like it's adaptable to all environments.
Yeah, and I think part of something that I think was brought up at one point is potentially like as we get into the more technical material of the course, there's going to be an opportunity to like write simple, like very simple algorithms, and I mean that's something that it's maybe somebody in the group wants to do for a certain week, and then they can share with the group. That could also be part of these lectures if somebody feels like doing that, though it's definitely not a requirement and by any means.
Thanks.
I have a quick question. So when you say simulation environments, are they mostly applicable to the gaming solutions? Like if you're coding for games, or usually RL started with the games, right? So if you have some custom problem that let's say you're trying to solve, the nutrient contents in a soil, or I'm just giving a example, but if you're trying to solve a custom problem, will these simulation environments still help, and could you give some examples on that?
I'm not sure if that's a question for me or whom, but yes, you always need a simulation environment, because you're interacting with an environment. And so the question is, how do you interact with that environment? The simulation environment, simulation essentially mimics the environment that you're working with, whether that's a robot that's trying to walk, or a stock market trading, or soil samples and the acidity and how that changes. That is the environment that you need to interact with. And either you need to code that, or if you can, get something off the shelf, like OpenAI or whatever.
I guess for the example that you said, the nutrients in a soil or something, you need a model which basically for any input that you give, your input is your action that we give, and for any input you give, it needs to give the an estimate, which is your observation in our case, but that estimate needs to be as close as to the ground truth as possible.
Yeah, I'd agree. I would be very careful with the word model, because if you're coming from deep learning or machine learning, traditional machine learning, the word model comes with a lot of baggage. So that's why we use the word simulation.
Okay, so I mean, like for the custom problem, you have to create those state diagrams, and if something is not available open source, then you by simulation environment, you mean you have to create all the states and the actions and stuff like that?
Yeah, think about a robot walking, okay? The simulation environment is just physics, okay? Gravity takes over, and you've got like Newton's laws. That's it. It's pretty straightforward. But that's the type of thing that you need to, the simulation environment needs to do. You need to provide feedback for your actions.
Yeah, thank you.
And another thing that I want to touch upon is like, so there are like 5 hands-on sessions. So I just want to, hear like, what is your expectation of your hands-on session? Like, is it fine if just some, so there are like 3 things, right? So one is DeepMind Acme package is there, which we can go over the examples, and the other is spinning up. So if you have seen the spinning up package, so there are like few exercises that we can solve, and it's available for both as a PyTorch implementation as well as like a TensorFlow implementation. But and then if you seen the post in the RL meetup channel, like there is a Halide challenge in Kaggle. So there's like 3 avenues that we can possibly explore. So the idea for the Halide challenge is to basically implement certain RL algorithms that we might cover in the class, and then see how it is performing with the other algorithms as such. So in that way, like we code it, and then we share the code with other people as well, and then talk about it. So like this is just like few avenues that we have thought. Like, is everyone okay with that, or if anyone has like other thoughts, please let us know.
Yeah, from my perspective, I think so we're still, I think we're still 9 or 10 weeks away from those hands-on things, so we'll have plenty of time to provide feedback of what we want. But I think kind of we could actually end up having like maybe a few different people doing a few different things based on their own interests, and we could come together and those people could share the small projects they worked on. But yeah, so I like this should definitely be a hands-on framework for. I mean, the best way to learn is to do. So I'm hoping to take some of the things we're learning over the course of this session and apply it to my job. So hopefully that works out, and I can share those things with you. But yeah, I think right now we have the OpenAI, the spinning up, which looks like it'll be pretty useful. But obviously we're happy to change based on feedback from the group. Yeah, go ahead, Tony.
I guess, right, I imagine the intention is not for the next 9 weeks for nobody to be trying anything on a computer and doing any programming, right? Even though there isn't any sort of thing hands-on scheduled in the study group. I assume people would want to be, trying to use what they've learned in the next 2 months, even before any hands-on session, right?
Yeah, correct. I think the way that could come to life is obviously not every week, but somebody's like, hey, I'm working on this thing, running into some problems. They could like present it almost as like a brainstorming session, or even just show something interesting that they did.
And in between Sunday meetings, that RL meetup on Slack would be the place to communicate?
Yep, I think so. Go ahead, Adrian.
No, I was just going to ask: is there a meeting between now and next week? Is there a midweek meeting sometime, or is this the incident?
Yeah, we did not plan midweek meetings. Just there's already so many TWIML meetings that people are multiple part of, so we didn't want to overload the schedule.
Okay, thanks.
There could be an avenue, I think. In the causal meetup, so they're doing like research paper reviews. That could be something we end up doing. Something I kind of noted here on the slide is this, like, especially the RL meetup channel, it should be a place to kind of collect resources from everybody's brains that they come across, other like interesting blog posts, research papers, things that are interesting, or like other resource that we can use for learning, and just like share that with everybody, so we can basically have a larger swath of information that we can bring to the table for these meetings. Looks like Sam asked an interesting question in chat about what's the way to go about creating infinite action space simulation environments. Is it something that would be based off first principles? And that is something I'm not sure of. So I'm used to the simulating based on first principles and like the physical sciences, as somebody mentioned. I'd be interested in if anybody knows anything kind of not based off of those, physics first principles.
Is this where we treat the problem as discrete rather than as continuous rather than discrete? So there are no episodes.
Sorry, it's Sam here. So yeah, my question was predominantly like around continuous action and continuous space, because now if I have some custom problem of my own to solve, which is of continuous in nature, then how do I go about creating simulation environment? Because like one way is to sort of like discretize the entire thing, like it's sort of like an approximate simulation, but maybe it's not the real reflection of the actual world, right, where my problem is going to be solved. So like how do people generally go about these things? Like,
I don't think it's, so I think we keep talking about this trading example, right? I think trading, especially like cryptocurrencies and things like that, have near infinite states. Like the price of that coin can be very precise depending on like how, like what percentage of the coin you want to buy. And in practice, it's okay to just allow that, like in your program, to just allow that to be a float. So your state is the price, whatever that is, and that's a lot of states. And you can take, if you had infinite money, or if you had a lot of money, you can spend any percent of that money essentially, which gives you a ton of actions to choose from. So I don't know that, I don't have the answer for how to do it, but it certainly is something that is done.
So in this particular example, you're just looking at the price aspect, right? Like generally in stock market, when you're trading, there could be multiple factors affecting the trades. Like it's a very complex problem, right? Just like weather prediction, it could be the price of oil, it could be how the economy is doing, it could be a lot of risk factors and things like that. So if you think about it, there's a lot of complexity. And then like when we try to solve, like let's say we are trying to have an RL agent build for portfolio management. So at that point, are you just like taking sort of like a estimate or approximation of some of these features and trying to build simulation out of it? Or like it's that's the point I'm trying to like understand. Like
I think, sorry, no, I was just going to say, so I think this is a function approximation. Are you referring to deep reinforcement learning, where we replace the table, the policy lookup table with a function approximation, which is at the core of deep reinforcement learning? So that is does somebody want to jump? So I think that's at the core, or that is an aspect of moving from a discrete to a continuous space. And that's how I understand deep reinforcement learning. The problem that it's solving is where you have a potentially infinite number of states.
Sorry, just to add to that, I think for a lot of problems, especially in robotics, what they tend to do is not try to model each and every aspect of the world. There's an emerging research being done primarily from like Berkeley that I'm aware of, that looks at kind of taking simulated models and applying them in real life, and looking at sample efficiency when it is transferred to real life. So that is one way of also thinking about that. Not everything not everything has to be a simulation. You could build a simulation which approximates many things and then transfer it to the real world and fine tune it there in some way.
I would suggest also that we shouldn't get confused. We shouldn't get confused between the agents and actions and the simulation environment. I'm no expert, but this is my view. The simulation environment is continuous. I mean, laws of physics, stock trading, whatever. I mean, there's an infinite number of states that you can be in, right? But as the actor or the actual agent, you have discrete number of actions and you have sequential actions that you take. But what you get back is an infinite number of possible states. potentially. And I think that's where the deep reinforcement learning comes into it. To keep things simple, we assume a discrete number of states, but there's no reason the simulation environment could not be continuous and infinite. Hopefully I haven't confused everybody.
Yeah, that makes sense to me. Thanks.
Yeah, that's helpful. I don't have anything further planned. People are free to ask whatever questions they have. I am going to, it looks like some good resources were put in the chat, so I'm going to save that and I'll post it in the RL Meetup channel and probably also add them to the Git repo when I look at it. But yeah, does anybody have any other questions or any other topics they want to talk about?
Yeah, I had a question. I mean, could I imagine that I can successfully use my Windows laptop and do what I want to do, or would I end up needing to go in some cluster somewhere?
I think it depends on, like, for most useful things, you probably will want to end up using a cluster to just cut down on training time, but more experienced people than me can probably chip in here.
Yeah, the OpenAI does not work well with Windows. So that might cause a problem. Like, it's there in the documentation itself. It's very hard to make it work in Windows.
Yeah, I would recommend using Colab, which is a fantastic free tool. Windows has so many limitations. PyTorch is one of them. I mean, for very simple stuff, it's good enough. I will use Colab, but if you want GPUs, there's some services out there who will charge you a nominal fee if every time you use a GPU, charge you per minutes. But I don't think you'll need a GPU for at least 9 weeks.
Yeah, and there's some resources on the Fast AI. Well, or as far as like GPU, like server hosting or access, there's some pretty economical options available.
Docker is an option. Docker containers might be an option. I'm not sure how well Docker runs on Windows though, but I don't think you can map your GPU to Docker. But that's what I use, and I find it very, very good.
You just have to get your hands really dirty. I'm not sure if if you want to.
Yeah, maybe it's not for everybody. But, yeah, definitely Colab is to get up and running right away. Yeah, I think Colab is probably the best bet.
I had a quick question.
I think Kaggle. Oh, sorry. I was gonna say I think Kaggle provides notebooks too.
Yeah, that's for the Halide challenge. So you can.
Oh, gotcha.
Actually, yeah, but not for general thing.
Gotcha.
So the OpenAI simulation environment works well on Colab?
Yeah,
is the question.
Yeah, you can run it up. Yeah,
okay.
It's just do a pip install on OpenAI. It runs fine.
Okay, great. Yeah, and for GPUs, I've been using. There's like a couple of them. There's Paperspace, which was mentioned by FastAI, and then there's a newer one is called Wash.ai, where where people rent out their GPUs. So I found Wash.ai. Like I'm always trying to, I have a limited budget, so Wash.ai is much cheaper. And I've tried Paperspace, I've tried Wash.ai, and I've tried. There's another one that Jeremy recommends. I think he's maintaining it now. Salamander.ai. Yeah, those three.
If I could just throw some advice, I went out there, I bought a laptop with a GPU, I spent $1,500. Everybody told me I was an idiot. I ended up like doing a dual boot. This thing's like about £5. And what I find is I really don't use the GPU that much. Most of my projects that I do are very basic. So don't spend money is my advice. Don't do what I did. Just use Colab, use the cheap stuff, and when you need a GPU, just pay the couple of bucks. I've got a $1,500 paperweight. I mean, don't do what I did.
Yeah, I'm the same. I have a $2,000 paperweight, which is just sitting.
Yeah, great.
Yeah,
I just. Go ahead.
Sorry, I was just going to change the topic a little bit. Did you want to comment on?
No, go ahead.
Okay, no, I was just going to ask, like, what's your experience of using OpenAI environments? Because I went down the path of using that a little bit, and then I switched to just creating the environment myself, because my own personal experience is that the creation of the environment is as, if not more important than the, like framing the problem than the actual algorithms, at least in getting started and trying to understand reinforcement learning. And I found the OpenAI environments, while they're quite good, in trying to learn reinforcement learning, they can just abstract away the aspects that are important to understand, like the idea of returning state, next state, reward, next reward, and the observations and all of that. So I'm just wondering what are the observations here of that? Did you jump in right away to OpenAI, or are you creating your own environments or using something else?
So I've made a couple for myself, okay. But always using the OpenAI like structure, their API, or however you want to call it. And that has worked okay for me. They're not, because I guess for me, and I'd love to connect with you after, Adrian, but I agree with you 100%. I think the environments is maybe, to me, the environment is the more interesting piece. But I've just taken the OpenAI structure and sort of re-implemented them. It re-implemented like my own environments in their structure.
Okay.
So then what benefit do you get out of the OpenAI? What does it mean, OpenAI structure? What does that give you?
I think the benefit that you would get is that it would allow you, at least as I see it, it would allow you to take advantage of other ORED algorithms that have been written for different environments if you follow that structure. Whereas if you do a more bespoke solution like what I've done, you can't take advantage of that. But now there may be tweaks might be required of each environment to allow it to work with the different algorithms, because no environment, I don't think, will be exactly the same.
And most tutorials and things are written using some OpenAI environment. Cartpole is a very popular one. Frozen Lake is another very popular one. So if you follow the same structure, it's helped me in debugging, because I can usually look at someone else's tutorial and say, oh, right, I forgot to update the state or something. Yeah.
Great. If anybody has any more questions, feel free to ask them. Otherwise, I was gonna stop the recording. We can reconvene next week. Okay. Sounds good. So I mentioned this earlier. There's a lot of good resources posted in chat. I saved it. I'll post them in the RL Meetup group. Joseph, do you have something that you want to ask?
No, I'm sorry. I just my microphone.
Okay. I just see the unmute, so I just call on those that unmute. But yeah, if not, we'll see everybody next Sunday, and I guess talk to everybody over the weekend in Slack. Good meeting, everybody.
Thank you very much for organizing this.
Thank you.
Thank you.
Thank you.